I'm about to start my stand-up show here. Unfortunately, I have no material for that. So instead, I will welcome you to the Education Policy Seminar. I'm Chloe Gibbs. I'm an assistant professor at the Madden School. This talk is part of the Education Policy Seminar series, which is sponsored by the Bankard Fund. And as many of you know, we sponsor a number of talks. So please see the Ed Policy Works site for those talks and join us for our next talk, which will be on Monday, November 3rd, same place, same time. Today we are delighted to have Kirabo Jackson from Northwestern. I'm very pleased to introduce him. He is an associate professor at the School of Education and Social Policy and a faculty fellow of the Institute for Policy Research at Northwestern. He's a labor economist. He received his Ph.D. from Harvard. And I'm sure many of you know his work on a number of education topics, including teacher effectiveness and match quality, incentives for student performance, effects of charter schools on teacher labor markets, single-sex schools, the list goes on. Today he's going to be talking to us about teacher effects on a broader range of outcomes than we normally consider, and it has important implications for how we think about teacher effects over the longer term. So I welcome.
Thanks for having me out here. It's a pleasure. Thanks for that really nice introduction. It makes me sound really yeah, so the paper I'm going to present today, some of you may have seen earlier versions of this, but it's a revised version of that earlier work. It's changed in some important ways. So the paper is called Non-cog and Mobility, Test Scores and Teacher Quality, Evidence from Ninth Grade Teachers in North Carolina. So the paper itself, the idea behind the paper is actually relatively straightforward, but as with most things, the devil's in the details, so I'll be talking about the details. So the paper itself is really motivated by this sort of first premise, which is that skills that are not captured by test scores matter a lot. So here's a quote here by Jim Heckman. It says, "The preoccupation with cognition and academic smarts, as measured by test scores to the exclusion of social adaptability and motivation, causes a serious bias in the evaluation of many human capital interventions." So the evidence on this is as follows. So we know that, I'm going to call them non-cognitive skills, by the way. I know some of you in the room are opposed to using that term. I'm aware of this. I'm not doing this to annoy you. It's just a term that's around there. I had to say something. So I'm just using the term non-cognitive skills. What I really mean by non-cognitive skills are sort of soft skills that are not well measured by test scores. So we can think of them as all those things that are sort of socio-emotional skills, socio-behavioral skills, soft skills, these kinds of things that we don't really pick up with standardized tests. But I will use the term non-cognitive because in my field that's what we call it. Sorry. All right, so non-cognitive skills not captured by standardized tests, such as adaptability, self-restraint, self-efficacy, and motivation, are important determinants of outcomes in adulthood. So this general fact, empirical regularity, has been documented both using data in the United States. It's also been documented using data outside the United States. There are a few studies using data from, I think Sweden is one of them, as well, where they had a really good battery of battery of tests to measure sort of how well it was designed for the military, actually, to measure how well the guys are going to like perform under, I don't know, fire. And this thing measured labor market outcomes to a great extent, above and beyond that we predicted based on test scores. There's another set, but these are also correlational studies at this point. They're just showing that having these skills when you're younger is associated with their outcomes in adulthood. The other piece of information is that there are interventions out there that we've seen that have either no effect or no lasting effect on test scores, but have large meaningful effects on adult outcomes. Some charter school papers have found this, some papers by Dave Deming, a recent paper by Chet et al., and a few others have found similar things as well. And also there's some evidence that the effects of some interventions on long-run outcomes can be predicted by their effects on non-cognitive skills. The most common salient one is a recent paper, no longer forthcoming, by Heckman, Tinkle, and Salvador that look at the early childhood interventions, and we find that basically the effects of these interventions on the non-cognitive skills was a much better predictor of the long-run effects in adulthood than the effects of the intervention on test scores. So the takeaway from this is that educational interventions produce both cognitive skills and non-cognitive skills, and both are probably going to be important for success in life. But unfortunately, only one of those things is well measured by test scores. So the idea behind this paper is to say, well, if that's true, maybe we can measure the effect of, in this case, teachers on this other set of skills that are not well measured by test scores, and if that's true, maybe we can get a better purchase on what the effect of teachers are in the long run above and beyond what we would know based on test scores. And that's basically the idea behind the paper. Pretty straightforward. And the key thing here is that we really don't care about test scores per se. It's obvious, but it's true. We don't. We really care about the effect of interventions on test scores because we think that effects on test scores is a good predictor of outcomes in adulthood. So if we can find something that predicts effects on adulthood as good or better than test scores, we might want to pay attention to that as well. And that's basically the motivation. I should turn my mic on so you can actually hear this later on. Hello? Wow. So existing studies on teacher quality really focus on test score effects. We're probably all very familiar with these studies. Some people in the room work on them right here. So, and one of the sort of takeaways from this literature is that teachers are one of the most important components of the schooling environment. So these studies basically show that having a teacher at the 85th percentile of the ability distribution versus one of the median is associated with about 8 to 10 percentile points higher test scores. The general finding in terms of standard deviations is a 1 standard deviation improvement in teacher quality is associated with about 1/10 of a standard deviation improvement in student test scores. And this is a relatively large effect. In a recent paper, which is very, very well known, Chetty and co-authors basically show that a teacher's effect on test scores predict adult outcomes later on, such as years of schooling and higher earnings in adulthood. I'll just step back for a second for some of you who may not, I'm sure most of you do, but when we talk about effects on test scores, what we're really doing is we're saying, let's look at test scores at the beginning of the year before a student's exposed to a teacher. Let's look at test scores at the end of the year after they've been exposed to a teacher for a year, and the difference between these two test score measurements is going to be a measure of how good the teacher was because it's a measure of how much the student learned over the course of a year. We do that on average for every teacher, and we get a measure of how effective that teacher is. That's all it is, and we call that value added. And what Chetty et al. Show is that teacher value added does actually predict, it allows us to identify teachers who tend to be better at increasing educational attainment in adulthood and earnings later on. They did this by linking data from like the 1980s to earnings data today. It's a really amazing combination of data. Another recent study, which some of you may or may not be familiar with, is a paper by Chamberlain. And Chamberlain, basically, Garrett Chamberlain got the exact same data that they used in the Chetty et al. Paper and basically documented that if you looked at the variation in the adult outcomes associated with individual teachers, that variation was about 4 times larger than that explained by test scores. Or another way to put it is the effect on test scores really measured about maybe 25% of the real variability in teachers on these long-run adult outcomes. So one question you might ask is, well, what is this other 75%? Sounds like a lot that is left unexplained. So while it's true that test score value added certainly is good at predicting better outcomes later on, and I'm not saying that they're not, it's not going to be perfect. And in fact, it's far from perfect. So the key thing is if the unexplained 75% is due to some unmeasured skills, this is going to matter a lot. First, because districts use value added for policy, so it's important that when we talk about a teacher being high quality versus low quality, we're measuring their effect on overall long-run outcomes and not just her effect on cognitive skills. Another thing, so we're going to possibly miss excellent teachers and reward bad teachers, and we might think in a world where we actually try to fire bad teachers, we could actually end up losing a lot of good teachers in the process. And when I say good and bad, I'm really referring to their effects on long-run outcomes as opposed to their effect on test scores. Basically, I'm making a disconnect between these two concepts where oftentimes we conflate the two as being the same. And I guess another implication is that, in the cases where schools or teachers have to produce outcomes, if these non-cognitive or soft skills are important, schools now have an incentive, or teachers may have an incentive, to divert efforts away from promoting these non-cognitive skills toward improving test scores if there's any trade-off that's been made between time spent on one task versus another. So the main objectives of the paper are as follows. So first, I'm going to present a factor model where student ability and teacher ability have cognitive and non-cognitive dimensions. I'm going to show, in the context of this model, that teacher effects on multiple short-run outcomes can predict long-run outcomes even if they're not correlated with themselves. Now, this sounds totally obvious when I say it out loud, but when I actually talk about it in terms of like teachers improving test scores and teachers improving attendance, people often think, well, they would have to be the same teachers. They don't have to be the same teachers, and the model basically lays out exactly why that's the case. And the other part, the other prediction is that we are going to be able to get a better prediction of a teacher's effect on long-run outcomes if we know what her effect is on both cognitive outcomes and non-cognitive outcomes simultaneously. The second part is I'm going to use this non-test score outcomes to form a proxy for non-cognitive ability.
And I'll go through exactly how that works in the context of the model. And I'm going to basically demonstrate the extent to which this non-cognitive factor predicts outcomes in adulthood, conditional on test scores. So this is just kind of saying, well, we know test scores predict long-run outcomes. Does this non-cognitive thing, which is just a weighted average of these non-test score outcomes, does that predict long-run outcomes? I'm going to show this both in administrative data and also in survey data that covers the whole of the United States to show this thing is replicable in those data sets. And then finally, I'm going to estimate 9th grade algebra and English teachers on test scores and also on this non-cognitive factor. And then finally, I will say, well, now that I've identified teacher effects on test scores and these non-test score outcomes, and we've shown you that these non-test score outcomes measure things that predict long-run outcomes, is it the case that teachers who actually increase these non-cognitive factors improve outcomes in the long run above and beyond that would be predicted based on their test score effects? And I'll show that that is the case as well. So you can all go. All right. So here's a theoretical framework. So basically, the model is such that there are 2 dimensions of ability. So each student I should just mention, I don't know what the protocol here is for like interrupting, but if you want to ask me a question or yell something at me, feel free. So each student I has a 2-dimensional ability vector labeled as sort of nu I C and nu I N. So C is for the cognitive dimension, N is for the non-cognitive dimension. And the key thing is that ability is not a unidimensional thing. Some students, so it's a multidimensional thing. You have cognitive skills and non-cognitive skills, and we're not making any assumption about whether they're correlated or not. So it's possible that some are high in both, but it's also possible that some are high in one and not high in the other. So every teacher has an ability vector, and the key thing here is that teacher ability here is not defined by her own cognitive skills or non-cognitive skills. I'm defining teacher ability as her ability to promote student ability in that dimension. So a teacher who improves students' non-cognitive skills would be a teacher who's high in non-cognitive ability, and a teacher who promotes students' cognitive skills would be a teacher who's high in cognitive ability. So the total ability of a student with a particular teacher is this, in this very simple world, the weighted average, or sorry, the sum of their incoming ability and the ability of the teacher. So in this simple context, so then the key thing here is that each outcome that we observe in the world is basically going to be a function of the ability of the student. So in this sort of really stylized world that we've laid out, we can think of a set of outcomes. So here's some short ones. So we might think that test scores are going to be a function of non-cognitive ability and cognitive ability. But let's just say, for the sake of argument, that it's all about cognitive ability. So in that case, we'd say that test scores are basically heavily weighted on a student's cognitive skills and is very unrelated to their non-cognitive skills. On the other hand, we might think of things like attendance. We're talking about high school kids, so students actually have some control over that. So we might think that a student who actually decides to come to school on time and not skip class may be very smart, but it's actually irrelevant for whether they're going to turn up for class. What that really is a function of is their sort of non-cognitive skills, whether they're going to stick to it and determination and motivation, and that's going to be a function of their non-cognitive skills. And you can think of, and basically every single outcome that we can observe for a student, we're going to think of as being some combination of their cognitive ability and their non-cognitive ability. Some outcomes are reflective of the non-cognitive ability, some of them are reflective of the non-cognitive ability, and some are reflective of both. And that's the basic idea. And the key, once we think about it from that perspective, what that means is that the long-run outcome, you might think of as being a combination of the two. I'm actually getting ahead of myself. So the teacher's effect here, in this case, we can think of as simply just being the weight of these betas multiplied by their ability. And the key thing here is that these weights determine the relationship between student ability and outcomes. So if we're talking about test scores, the weight on the cognitive piece would be high, the weight on the non-cognitive piece would be low. And if we're talking about attendance, the weight on the cognitive piece would be low, and the weight on the non-cognitive piece would be high. So the only reason why we see different outcomes in this simple model for different students is the relative weights. So a teacher's effect in the long run is going to be a function of how much so key thing is the long run outcome is also going to be a function of these two dimensions of ability, and a teacher's effect in long run outcome is just a weighted average of how she affects ability. And the key thing here is that the long run outcome is not observed, but the policymakers want to predict teacher effects on the long run outcomes. That's the key thing. So one implication from that is that a teacher's effect on a long-run outcome may be correlated with her effect on multiple short-run outcomes, even if her effect on those short-run outcomes are not correlated with each other. Like I said, this is an obvious statement, but oftentimes people don't think of it that way. So the example here is teachers who improve test scores also increase wages. We know this is true based on the Chetty et al. Result. Teachers who improve self-esteem may also increase wages. I don't know if this is true, but it's certainly a possibility. Now, teachers who increase test scores do not necessarily have to be teachers who increase self-esteem. Logically, these three things can exist simultaneously, so hopefully no one's going to come in like 20 minutes and be like, well, how is it possible that these two sets of teachers aren't the same? It's because they don't have to be the same. It's just logically not the case. They have to be the same. So the second prediction is that one can predict a greater fraction of the variability in teacher effects on long-run outcomes using two short-run outcomes or multiple short-run outcomes that reflect a different mix of both kinds of ability than you can get using any single short-run outcome. So, for example, this sort of, you go for the paper, there's a math in there, but basically if you regress the teacher effect on the long-run outcome on her effect on outcome one, let's say outcome one is test scores, then the residual, what you can't explain using her effect on test scores, is going to reflect her effect on the ability that is in the other dimension. So the residual, the unexplained piece, is going to be potentially the teacher's effect on the non-cognitive skills plus some noise. So what that means is, basically what that means is if the residual is correlated with the teacher's effect on another outcome that picks up that non-cognitive piece, then you can actually explain that residual. And that means you're explaining more of the overall variation. So this is just laying out that argument. So apart from sort of the trivial case where, you know, the long-run outcome is only based on cognitive ability or only based on non-cognitive ability, or the trivial case where like the two outcomes you're talking about are exactly the same or linear functions of each other, as long as they're different, they measure different skills differently, we should be able to get a better prediction on the long-run outcome using two short outcomes. Okay. So the data I'm going to use come from North Carolina. So I have data on all 9th grade public school students in North Carolina from 2005 to 2010. And the data come from the North Carolina Education Research Data Center. So the student data include demographic characteristics, transcript data, so I know the courses that students took, the grades that they earned. I have their middle school achievement, so their grades at the end of 8th grade prior to 9th grade entry. Their end of course scores for Algebra 1 and English 1, so this is a standardized test that is given across the whole state in Algebra 1 and English 1. And then it also includes some other outcomes such as suspensions, absences, and code that allow one to link students to their individual teachers. So data are linked, so these data are also linked to dropout and graduation and SAT outcomes for the 2005 through 2009 grade cohort. So obviously, for the earlier cohorts who took it in like 2010, at the time when I was analyzing the data, they were still at school. So I can only analyze it for the earlier cohorts. So I'm going to limit the analysis to students who took either Algebra 1 or English 1. The reason is these are the two most commonly taken courses. I didn't want to deal with situations of selection. There's enough selection issues to deal with as it is. And I only look at the first time a student is observed in 9th grade. The reason is that exposure to a teacher, if it causes you to repeat a course, then that's going to be endogenous. So to avoid that sample problem, I'm only going to be looking at the population of first-time 9th grade entrants. So the data cover 464,502 9th grade students in 619 schools in classes with 4,820 English teachers and 4,432 Algebra 1 teachers. So this is what the data look like. So there are a bunch of variables here, so I'll just focus your eye on a few key ones. So the main short-run outcomes I'll be looking at are the Algebra 1 score in 9th grade and the English 1 score in 9th grade. The non-test score outcomes I'll be looking at will be the natural log of the number of absences the student had over the course of the year, whether they were ever suspended from school, either in school or out of school suspension, their GPA, and whether they ended up being on time in 10th grade. That basically means if they earned the data in 10th grade the year following 9th grade entry. So these are the four main long-run outcomes, and then we have the test score outcomes as well. Sorry, non-test score outcomes. The longer-run outcomes I'll be looking at to see whether these short-run effects on these short-run outcomes affect long-run outcomes are basically whether the student is a dropout and whether the student graduated. One point here is that anyone who's worked with dropout data knows that the data are notoriously difficult to deal with because it's very hard to verify whether someone dropped out or just like left the state or something like that. So it's helpful to look at these both together. So I look at both dropout and graduating. Also, I look at whether the student took the SAT. This is sort of a secondary outcome. I look at that as well. We might think of that as like being a good predictor for whether you go to college. It turns out in administrative data, it certainly is. And also, when they graduate from high school, every student in the state actually takes a survey that asks them whether they intend to go to college later on. This thing is very highly correlated with the SAT, so it's almost measuring the same thing, but there's sort of proxies for intentions to go to college, which are highly predictive of going later on. Okay. So the first thing I'll sort of point your eye to is the basic correlational structure of the data. And I think there's some things that I saw when I first looked at this that I was surprised to see. So the first thing that jumped out at me was this kind of how low things are correlated with each other. So if you look at the number of days absent, as you'd expect, the number of people who have more absences are more likely to be suspended. So these are correlations. Correlation of 0.19. Negatively correlated with grade point average. So people who tend to be absent tend to have lower grades. Sort of expect that. And they're also less likely to be on time and grade. And they tend to have lower test scores. But the key thing is here, the correlations are not super, super high. Another thing here is if you look at the correlations between days of being absent and your test scores, they're super low. Negative 0.097, that's almost like you're uncorrelated. So same thing happens if you look at other outcomes. So look at being suspended, the correlations are generally no, but the correlation between being suspended and the test score outcomes is even lower than for the other stuff. We see a similar pattern over here, not so much for grade point average, but we see it for all these things as well. So the takeaway, the first thing that I noticed was that this idea of having this sort of model star student who like is amazing in all ways, not only are they smart, but they're also very well behaved, they never get sent to the principal's office, they're always on time, and they're never skipping school, that doesn't just seem to be borne out into data. So this sort of is more consistent with the multi-dimensional ability model and less consistent with this unidimensional model that I think economists often have walking around their head. It's much more consistent with the fact that there are different kinds of people. I don't know what kind of students you guys were. I know personally I was kind of a troublemaker. I always had great grades, but I was definitely probably, well, I know I was suspended a few times. Probably. So I would be, people like me probably generate this correlation being lower than it might have otherwise been. And we can all tell stories. We also know people who are, very, 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 very bright, who don't end up doing so well later on because they just don't apply themselves. That's also very common. So this is the first thing that sort of jumped out at me when I looked at the data. In fact, I was so surprised by this. I looked in the NAILS 88, which is a nationally represented data set, and it's pretty much the same thing. Test scores are not super highly correlated with non-test score outcomes, which means that there's probably two dimensions of ability that you might want to think about. Yeah?
And these aren't going to be driven by outliers, because I can imagine here, right, that you would have several outlier cases that really could kill these things.
I mean, we're talking 400,000, we're talking about 500,000 observations here, so I don't think this is driven by outliers. And like I said, this is replicated in other data sets as well.
It was sort of a similar question. I guess I was wondering what happens when you sort of put it in, say, district fixed effects for this kind of thing.
Same thing. Yeah, so it turns out when you stick in, so if you control for stuff, correlations just get smaller.
Really?
Yeah. Which makes sense. I mean, we might, you might see that like the geographic regions or schools where we have very high test scores tend to be worse on these measures. So once we account for that, these correlations just get even lower. So, like I said, when I saw it, I was like, this is strange, but it's just the way the data look. It's just not the case that everyone is, and basically, if you do a factor analysis on this, you're going to find two principal factors, well, at least two principal factors, you're not going to find one. So the data are also rejecting just one underlying factor that's generating covariability across these data. Yeah.
So all of these are noisy measures of whatever underlying thing
Yes.
they're measuring. So how much would, imagine you could actually measure cognitive skill, you
Yeah.
could actually measure non-cognitive skill,
Mhm.
but they're noisy. I mean, how much of that, when you get low correlation just because of the noise?
Yeah, so you're exactly right. So certainly these are definitely noisy, and that's definitely going to affect it. But so I would say the fact that there's noisiness would explain why the correlations are generally low, but it doesn't explain why the correlations with test scores are always lower than the correlation between test scores and these behavioral outcomes is low, because lower than they are among the behavioral outcomes themselves. Does that make sense? So another way to say that is the fact that GPA is much more highly correlated with absences than test scores is not going to be explained by noise. And that's really where I'm getting at, which is that the non-test score outcomes are nothing's highly correlated with anything, but the non-test score outcomes are much more highly correlated with themselves than they are with the test score outcomes, which kind of suggests that there are test score outcomes that are loaded on one factor and non-test score outcomes that are loaded on another factor. Does that make sense? Yeah. But you're right, the noisiness generally is going to affect the overall load level of correlation. That's exactly right. And some of these things are binary too, which is going to certainly affect that. Okay, so what I did here was I said, well, we have a lot of these short-run outcomes. Let's summarize this in a simple way. So what I did here was I created this non-cognitive factor, which I'll be using a lot. So all I'm doing here is I'm saying I'm going to create a weighted average of all these non-test score outcomes to create one variable that I can look at. And these are exactly the weights. So basically what it is, the non-cognitive factor is 0.64 times GPA plus 0.57 times being in 10th grade on time, minus 0.33 times suspended, because that's a bad thing, so we have a minus sign in front of it, minus 0.45 times the log of absences, again, because it's a bad thing, we have a minus sign in front of it. So this is just a weighted average of all these short-run, non-test score outcomes. The way that I constructed this specifically was by doing a factor analysis. I just ran a factor analysis on these 4 non-test score outcomes, and I took the first principal factor, and those were the factor loadings that I came up with. So it's sort of this underlying factor that explains covariation across these things. And then the second thing was to say, okay, now that I have this factor, what I call a non-cognitive factor, what happens, how much of the variability can I explain in terms of test scores and the non-test score outcomes based on the factor versus test scores? So what I have over here is just an R squared. So this is the R squared of math scores versus absences, and as you can see, the R scores are very low. Math scores explain very little of the variability, and absences is being suspended. It explains about 30% or 35% of the variability in GPA, which makes sense. And then very little of anything else. And of course, it explains a lot of variability in English scores as well. So when you look at a non-cognitive factor, this is just showing you that it is picking up a good amount of what's going on. It explains about half of the variability in absences, 25% of the variability in suspensions, 70% of the variability in grades, 40% of the variability in being on time. And it is correlated with test scores. So our intuition that like good students tend to be better in all these dimensions is generally true, but correlation is far from 1-to-1. So here it's about a quarter of the variation can be explained that way. Okay, so this is just saying, well, now that I have this thing, can I predict log-run outcomes with it? So this is using the same administrative data. Here, can I predict dropout using these non-test score outcomes and test score outcomes, and everything has a bunch of stars on it, which is saying everything is significant at the 1% level. And yeah, students with higher grade point averages are less likely to drop out. Students who are absent, more likely to drop out. Students who are suspended, more likely to drop out. On time, less. Students who have higher test scores, less likely to drop out. You can see the data, it's all there. But the key thing is, the test score outcomes predicted, but the non-test score outcomes do as well. This is not really new, but it's important to show. Down here, all I've done is I've replaced the non-test score the 4 non-test score outcomes with a single non-cognitive factor and run the same regression. These are all standardized now to be mean 0, variance 1. And what this is saying is increasing math scores by 1 standard deviation reduces the probability of dropout by 1.2 percentage points. Increasing the non-cognitive factor by 1 standard deviation reduces the likelihood of dropout by 5.7 percentage points. Now, if you looked at that, you might say, well, this means that non-cognitive ability is much more important than cognitive ability in explaining these things. One might say that. I'm not going to say that because I'm going to get in trouble, but one could look at that and make that inference. But it certainly suggests that the non-cognitive factor matters. Yeah.
So I don't understand why GPA is in the non-cognitive. I mean, I don't know where it goes.
No, it's, yeah, so
combination. So I would have thought you'd want to take that out and do it just with the other 3.
Yeah, so it's a good point, and one that I was hoping I wouldn't have to talk about, but I will. So basically, so if you go back to the factor analytic model, basically what's happening is there are 3 kinds of variables. There are variables that load very heavily on the cognitive piece, which are test scores. There are variables that load very heavily on the non-cognitive piece, which are absences and suspended. And then there are variables that weigh somewhat a bit on both, which is what the model says. The model says that some variables are going to have weights that are more evenly matched, and GPA is one of those. So GPA and being in 10th grade on time are the two variables that have a good amount of weight, both on the cognitive piece and the non-cognitive piece. So you're right, but it's not a cognitive measure. It's not a non-cognitive measure. It's a combination of the two. And this is consistent with the way that we think of grades. So if you look at sort of the way the studies on grades and how teachers assign grades, I think it's like the 3 Ps or 4 Ps, and I'm going to get them wrong. Yeah, so one is performance, the other one is products, the other one is process, I think, and there's a 4th P that I can't remember. Yeah. But basically, you might think the student who's motivated and is going to like say, oh, I'm sorry, I screwed up on the test. Can I do some extra work? They're going to still get an A, even though their standardized test scores would be low. And that's why it's picking up a lot of this underlying motivational non-cognitive stuff as well. Does that make sense?
Well, it does, but it seems to me that you shouldn't put it in the non-cognitive group. You should just take it out.
Well, I'll show you results that use each one of these things individually. And the key thing is not so much that so I don't want to get into much of a conversation about what's cognitive and what's non-cognitive, because that's really more of a measurement issue. The broader point is that like it's not test scores, and it's not measured by test scores. So what I'm picking up is the GPA certainly has information about non-cognitive ability that test scores does not pick up, and is that valuable at all in terms of predicting teachers? And that's really the big picture motivation for using it. Not so much to say whether this is cognitive or not cognitive. Does that make sense? So that's, but I understand what you're saying. Yeah.
So to what extent is this, because the non-cognitive factor is going to be a combination of 4 or 5, right? Different covariates. So is it much more reliable to measure? And so is it a difference of measurement error between the cognitive and non-cognitive?
That's a good question, and it certainly could be. It certainly could be. So, and this is the thing. I definitely don't want to be like, oh, I'm measuring non-cognitive ability. As my voice booms over it. I'm not saying that. What I'm really saying is that it is a measure of it's a measure of non-cognitive ability to some extent. It's a proxy. And I'm not saying it's the measure or the best measure. And there are a whole host of reasons why a simple comparison of these two things are going to be wrong, one of which is that this is not causal. This is just correlations in the data. But people look at correlations in the data all the time and infer from it. And one of the motivations for thinking test scores are really important is exactly this kind of correlational data. So I'm just saying if that's the argument for looking at test scores, let me lay down a similar argument for the non-test score outcomes to see what that looks like. But you're absolutely right. One would be cautious to interpret any of this in a super causal way, which is why I'm not going to do it. And I'll show you stuff that's going to be causal later on. So over here, so I'll just skip over. So basically, this is showing you the same thing using the NELS 88. So if I use the NELS 88, which actually has outcomes even further along in someone's development into adulthood, I have test scores in those data, but we also have exactly those same non-test score outcomes in those data as well. I can construct that same exact factor. And if I do that, I won't spend too much time. What you find is that dropout is very highly predicted by the non-cognitive factor. It's actually not very predicted based on the math scores. You can see here in these data, it looks different. The estimates aren't that different, but test scores do predict it, but the non-cognitive factor is much more predictive of dropout. Same thing happens over here. Graduation, the non-cognitive factor matters more. For college going, both of them matter. The non-cognitive factor seems to matter more. If you look at arrests, as you'd expect, a non-cognitive factor, being high in the non-cognitive factor reduces the likelihood of being arrested by about 5 percentage points. This is significant at a 10% level of positive effect. I don't know what's going on here. Smarter people are more likely to be arrested. Not quite sure what's going on there, but it's only significant at 10% level. It could just be sampling variability, or maybe there's something to it. I don't know. Likelihood of being in the labor market, positively associated with both these things, and the likelihood, and just in terms of earnings, both of them matter quite a bit. The non-cognitive piece matters a little bit more. Second thing I do, just to be like, well, I've measured this thing, I've labeled it non-cognitive ability to behave like non-cognitive ability. So I say, well, if you look at other studies of non-cognitive ability, one of the findings is that non-cognitive ability matters a lot for the bottom end of the earnings distribution. So using the NELS, I can actually see, based on this measure that I've put together, does it behave the way we expect it to behave? And in fact, it does. So if you look at the national log of income, the 25th percentile, 50th, 75th, and 90th, what I find here is that the non-cognitive factor has a very, very, very large effect on natural log of income at the lower end of the distribution, and the marginal effect falls as you go higher up in the distribution. While cognitive ability, sort of the math Z score in this case, sort of matters all the way through and matters less at the bottom end of the distribution, which makes sense. At the bottom end of the distribution, it's not so much about how smart you are, it's about can you actually just show up to your job on time and not piss off your boss. So this is sort of consistent with that, and this is just a way to sort of validate the measures that I have in these data to tell you that this is something real and not just some funky statistical artifact. Okay, so the next step is to actually identify teacher effects on test scores and also teacher effects on this non-cognitive factor. So I'll lay out the empirical strategy for that. So I'm going to model outcomes of student I in class C with teacher J in track G at school S in year Y with this equation right here. So to make life easy, I'm going to have an outcome that's going to be a function of lagged achievement. So I am including lagged achievement here as a covariate, but it is actually not my key condition variable, to be clear. I'll talk about that in a second. There's a set of covariates: parental education, gender, ethnicity. There's going to be a teacher-specific intercept. This is basically teacher fixed effect. The important variable here is actually going to be the track-specific intercept. So I'm going to define a track as being the unique combination of the 10 academic courses that students must take and the school. So everyone who's in the same track took exactly the same set of academic courses in that year, and we're at that same school in that year. So that's the way we define track, or I define track. And then there's a school by year effect, just to pick up any transitory stuff. This is going to be particularly important when we talk about things like graduation. So if there's like a really good year and graduation rates are high, I don't want to have that mess up my estimates of teacher effects, so I'm controlling for that explicitly. There's a classroom intercept here and a random error. So because I have my measure is going to be the school track, overall, that's right, see more complicated. So it's the 10 largest academic courses and the level of Algebra 1 taken and the level of English 1 taken. So another issue here is that when we talk about English and algebra, there's going to be an honors algebra, there may be a regular algebra, there may be an accelerated algebra, so I'm going to control for that as well. So everyone who's going to be compared took exactly the same level of algebra, took the same set of 10 academic courses, and went to the same school. So that's the measure of track. So you might think, well, it sounds like you're parsing the data super, super thin. How can you possibly get an identification? So there are about 17,000 or 18,000 school tracks. But the key thing is people don't choose tracks randomly. Like someone doesn't say, I'm just going to throw darts at the board and those are the courses I'm going to take, right? People do things in clusters. There's a natural set of courses people tend to take. So if you look at the data, there are only about 3.7 students who are in singleton tracks. If you compute probabilistically, the likelihood of that just by random chance is much higher. So over 60% of students are in tracks with over 50 students, and the average student is in a track with 104 other students, which makes sense. People take classes in general predictable ways. So because the main models include school by track effects, all the inference is made within school tracks. So the identification of the teacher effects really comes from two sources. One is we're going to be comparing the outcomes for students of teachers at the same school, teaching students in the same track at different points in time. So for example, the Algebra 1 teacher leaves in 2005 and is replaced by another teacher in 2006. That's going to be one source of variation. The second source of variation is comparing teachers at the same school, teaching students in the same track at the same time. So that would be, we have multiple Algebra 1 classes and a bunch of students taking a bunch of courses, and we're only going to say, well, if we have a bunch of students taking the same courses, some are taking Algebra 1 with Mr. Smith, some are taking it with Mr. Jones. That's going to be a comparison. What we're not going to be doing is comparing this teacher to some teacher who's teaching the honors kids. That's not going to happen. And we're not comparing them to some teacher teaching some other class. Yep?
It's really common for students in honors classes to study Algebra 1 in 8th grade.
Yes.
Are they in your sample?
So I'm not using 8th grade at all. So the sample size for English is larger for exactly that reason. There's a lot. So there is some Algebra 1 taking in 8th grade. That's right. So the population of Algebra 1 students is all 9th graders. And in terms, so I forget exactly what the portions are. I'm guessing that affects again maybe 15% of the data set. So they're not included because it's just a different population. But the English 1's results are going to be for all teachers.
Okay,
because
I was just wondering if that would leave your high achievers out, but
It might. It might. It certainly could. Yeah. And I'll show you some results that do differ by English versus math, and we can come back to that and maybe explain some of that difference. Specifically, the English effects are really strong and the math effects are weak. So I don't know if that's right. I mean, it's potentially something that's going on. Okay. So the game here is to say, well, once we've identified teachers who we know improve cognitive skills or improve non-cognitive skills, are these the same teachers that actually improve long-run outcomes? So in order to do that, you need to basically correlate the teacher effect on the short-run outcomes with the effect on the long-run outcomes. Now, one can do that in a simple way by simply saying, okay, well, this teacher had high value added, and I want to see how well her students did 4 years later. The problem with that is that it's going to lead to a mechanical bias. Because let's just say by random chance, a teacher could have high value added because she happened to have an unobservably great crop of kids. So her value added is high, and those unobservably amazing kids are also going to be more likely to graduate from college. So what we don't want to do is use the same sets of students that we use to estimate a teacher's value added on test scores to estimate her effect on the long-run outcome. So what we need to do is to get an estimate of a teacher's effect on the short-run outcomes using a different set of students. So what I'm going to do is basically get the estimate from out of sample. So in principle, what I'll be doing is I'm going to say, for every teacher, I'm going to say, how good was that teacher historically at improving student test scores or improving a non-cognitive factor, and how well is she doing with her current kids, based on how well she has performed with different kids. And that's basically the game. So it's very similar to the Chetty et al. sort of strategy of using out of sample. So I'm going to predict how much a teacher improves student test scores and a non-test score outcome in a given year based on her performance in all other years, where she was dealing with a completely different set of kids to get rid of that mechanical endogeneity. So in the first stage, I'm going to estimate this beast. There are going to be no teacher indicated variables, so the overall error term in this model is going to basically include a classroom effect, a teacher effect, and an idiosyncratic error term. Then what I'm going to do is I'm going to compute the average student level residual for every teacher. So I'm just going to take the out of what's unexplained at the teacher level, and that's going to be my sort of blue estimate. That is my best linear unbiased estimate of the teacher, but it's not my blow. It's not my best linear unbiased prediction of how well a teacher is going to perform. So I'm going to do here, take my blue, and I'm going to turn that into well, it's probably not a blow, but into a prediction. So in the second stage, I'm going to take the predicted effect of a teacher for the current year, where I've used all other years of data, and I'm just going to run a regression of her outcomes today, and stick in the estimated effect from other years, and then I'm just going to take the fitted values from this as her predicted effect. So mechanically, what I'm doing is, once I have this thing, if I stick this thing in a regression, the coefficient is going to be 1 if I'm looking at the same outcome. So once I take this prediction, if I want to predict a teacher's effect on test scores based on my predicted effect on test scores, the coefficient of that is going to be 1. But the nice thing about that is, when I stick it and try to predict some other outcome, it leads for very natural interpretation, because it means I can say the coefficient on that is the effect of a teacher who improves the test score by 1 standard deviation is going to be the estimate, the coefficient on that other thing. So it's helpful for interpretation purposes. And just to be clear, the prediction of a teacher's effect, all it is some scalar multiplied by her fixed effect using all of the data. And if there were no estimation error at all, then they would be one and the same. The only reason they're different is that there's some estimation error, and this is just inflating it to have a coefficient of 1 in the estimation sample. Is that clear? Yeah. So the second thing is to assess selection of students and teachers. So this, issue always comes up. So the key identifying assumption in this paper is that teachers are randomly assigned to students within school tracks. So the key conditioning variable that I'm using here is actually the school track, and it's not prior achievement. This is important to make clear. And the reason this is important to make clear is that you might think, well, if you're predicting teacher effect on test scores and you're controlling for lag test scores, that's a really good proxy. If you're trying to predict teacher effect on GPA and you're not controlling for lag GPA, it's not really a fair comparison. So I'm not going to rely on lag test scores as being a key conditioning variable. The key conditioning variable is going to be the track. And it's actually not a bad key conditioning variable because you might think, basically, people are going to select the tracks, but once they're in the track, they're not going to select the teachers that much. And that's basically the idea. So to assess the degree to which there is selection on observables within school tracks, what I do is I predict each outcome. So for every outcome, let's say I want to talk about math test scores or any of the other non-test score outcomes, I can take that and I can run a regression of all the covariates, like their incoming test scores, their gender, ethnicity, all these parental education, and I can predict how well that student would be expected to perform for that outcome, and that's going to be their predicted outcome. And I want to see if that predicted outcome is correlated with a teacher's out-of-sample estimated effect. And that's going to give me an estimate, a sense of whether there's selection or not. And in fact, so if that thing is positive, it means there's positive selection. If it's negative, it means there's negative selection of teachers to student ability. If there are no selection of students to teachers by ability within school tracks, so once I condition on school tracks, there should be no systematic relationship between the predicted outcomes and predicted teacher effects, and the coefficient would be equal to 0. And I wish I could tell you that's what happened. That's not what happened. So when this test is actually implemented, there's clear evidence of positive selection. So there's definitely some evidence that on average, if you look at the entire population of schools, teachers who have higher predicted value added tend to be associated with students who have higher predicted outcomes based on incoming characteristics. So that's a problem. So the way I'm going to deal with it is to reduce my estimation sample to a sample of schools where that doesn't happen, is basically going to be my approach. So essentially, the idea is if all schools always had all their best teachers in with all their best students, I'd pretty much be out of luck, because then there's nothing I can do. But if we think that some schools practice positive selection, some don't practice any selection at all, and some may actually practice negative selection, then I can actually deal with this issue by removing the worst offenders in the positive selection so that on average I get a 0 correlation in my data. And this is exactly what I'm going to do. So for every school, I can regress the teacher value added on the predicted outcome, and for every school, I'm going to get a t-statistic for that test. And what I'm going to do is basically basically I'm going to do that and say, well, there's going to be some t-statistic at which, if I eliminate all schools with t-stats above that, the correlation in the remaining data set is going to be 0. And that's what I'm going to basically do. So I'll just show you what it looks like. So it looks like this. So this is the, on one axis, this is the actual coefficient of the predicted teacher effect on the predicted student outcome. And just for frame of reference, this thing would be equal to, the coefficient of this is equal to 1 for the actual outcome. So what this is saying is if we use the full sample, we get a coefficient here of about, it's pretty big in this case. No, oops, over here. The coefficient over here is about 0.15. So if there was no effect, it should be 0, but it's about 0.15. And the coefficient on the real effect is 1. So about 15% of the effects might be messed up by error if you use the overall data set. But if you keep on dropping schools that have smaller and smaller and smaller t-statistics, once you get to a t-stat of about, I think it was like 1.8, then the correlation basically ends up being 0, and t-stat is 0. So I mechanically basically ran this model, keep on dropping samples again and again until I got to that point where it's equal to 0, and then that's where I stopped. And once I did that, that basically dropped about 20% of the sample. So that ended up being my English sample. For English, I did the same thing for math. For math, the selection was much less severe, and here I ended up using about, I think, 85 or 90% of the sample. But the strategy was the same, yeah.
So this is cool, but I'm wondering why I'm wondering why you didn't just use the first source of variation that you identified, the teachers switching across the school tracks over years.
So one could do that. The reason is this, like, it's a data issue. So the project needs data, and it's not like I'm have tons of power. It's like, yeah, I'll just drop all that variation. So that's basically the reason. But you're right. I mean, certainly one could focus in only on the cross cohort variation, and I'll show you some results that use exactly that source of variation, and you'll see that they are very similar. But I use that as a robustness check rather than using it as my identification strategy. But you're thinking exactly right. So now that I've sort of zeroed in on a sample where selection on observables is no longer an issue, of course you're like, well, you just haven't dealt with selection on unobservables. So to assess that, I'm going to implement the Chitty test. And basically the idea is that if the estimated effects capture only student selection of teachers within a track, then if we average everything, if we average teacher quality at the track level, and we run a regression of the average track level teacher value added against student outcomes, the coefficient on that should be 0. Specifically, if a teacher is good, because if a teacher is thought to be good because she gets all the better kids in the track, and another teacher is thought to be bad because she gets all the worst kids in the track, then if we just said, well, let's take the average value added for the entire track and regress that on the average effects of average test scores, the coefficient on that would be 0. If, on the other hand, the value add is picking up not just selection but other stuff, that coefficient will not be 0. And if, in fact, it was perfect and there was no selection at all, then the coefficient using the average would be exactly equal to the coefficient using the individual treatment level itself. And that's basically the idea behind this test, and that's what I'm going to do. So if you look at this table over here, in the top, I've already told you what I did. So the fact that there's 0 correlation between predicted algebra scores and the actual predicted algebra effect, and the predicted non-cognitive factor and the actual predicted cognitive factor, 0 is entirely unsurprising. But this is just to show you that this holds in data once I've made that sample restriction. So down here, this is dealing with the selection on unobservables. So if you look at the predicted effect using all the variations, comes to your question before, we get a coefficient of exactly 1. Not surprising because it was constructed that way. The second thing is, well, we can look at the predicted effect using the variation within a track. And that is to say, we're going to, and this is by conditioning on school by year, by track, and only saying, we're only going to compare 2 teachers who are teaching exactly the same school in the same track. So only within track variation, and the coefficient on that is 0.981, which is almost identical to 1. And then we can say, let's only look at variation across tracks. And that's kind of the suggestion you have. So we aggregate everything at the track level, and we get a coefficient of 1.051. This is for the algebra test scores. Again, very close to 1. And then finally, this is just to be like, well, since we're aggregating, let's just go all the way up to the school level. So this is the school year mean, and we see the coefficient here is 0.964. So everything here is close to 1 for algebra scores. For the non-cognitive factor, again, things are close to 1. You can't reject that they're 1 for all these things, suggesting the selection is not really a big issue. Same thing here for English and over here. One thing to point out is if you look at the non-cognitive factor for math and English, you can see things are very strong for English and pretty weak for math. In fact, for all the aggregate level results, the coefficients, I mean, they're not 0, but you cannot actually statistically distinguish them from 0, which either means that the non-cognitive factor is not a very strong thing for math teachers, or, yeah, that's probably what it means. And we'll see some evidence of that over here. I mean, it does work here, but over here. For English, when you aggregate, in fact, the point estimates actually grow, they get larger, and they are definitely statistically significantly different from 0. Okay. So hopefully this has convinced you that there's no selection in the stuff I'm going to show you. Okay. So the first thing I'll do is just show you the standard deviation. How much do you have time, by the way?
35.
Okay. So I'll show you the standard deviation of teacher effects. Thank you. Just to give you a sense of how big these effects are. So I have another paper that goes into some detail about how large teacher effects are when we control for tracks. So I won't go into that detail here, but basically, if you control for the school track effect or the year effect, we find that the estimated, well, one thing you see is, first of all, English teachers aren't really affecting math scores at all, math teachers are not affecting the scores at all, which is, I think, good, if we're going to believe the results. And the English teacher effect, the math teacher effect on math scores is about 6% of a standard deviation. It's a little bit smaller than we're typically used to seeing. I argue that this is because we're controlling for track, and this is just showing you what happens if you don't control for track. It's about 13% of a standard deviation. If you do, it falls by about half. But then, more importantly, if you look at all these other non-cognitive outcomes, and this is one reason why I aggregate, turn everything into one index, is we see effects that are sort of good size. Standard deviation is about 1.5% for suspended, about 0.04 grade points. For GPA, we see effects here. And then if you just look at the non-cognitive factor, one standard deviation improvement in teacher quality is associated with about 7% of a standard deviation increase in the non-cognitive factor. So the teacher effect on a non-cognitive factor and the teacher effect on a cognitive factor seems to be about similar in size for the algebra teachers and similar also for English teachers. This is what that's showing. Okay, so now that we have these estimates, one question is, are they correlated? How much can we explain? So this table is basically arguing or showing you that teachers who are predicted to improve the non-cognitive factor are not the same teachers who are necessarily predicted to improve test scores. So what I've done here is I've estimated a regression predicting each outcome as a function of the teacher's effect on algebra test scores or English test scores and a teacher's effect on the non-cognitive outcome. And the R squared is obviously just the fraction of the variability in the effect that you can explain. So this is saying that about 5.7% of the teacher's effect on the algebra test score can be explained by her effect on the non-cognitive outcome. So this is sort of the main finding, which is that they are not the same sets of teachers. So in fact, even though the non-cognitive factor and test scores have a correlation of about 0.2, and I think that there it's maybe 10% can be explained, when you talk about the teacher's effect on these outcomes, it's even less. And this is just showing you here that the teacher's effect on the algebra test score is explaining less than 1% of the effect on suspensions, less than 2% of the effect on absences, 8% of the effect on GPA. So this is sort of getting a little bit at your issue about, is GPA just really a cognitive thing? It's not. And well, it's not just cognitive, in the sense that the effect on test scores explains only 8% of the teacher's effect on GPA in comparison to the non-cognitive factor, where teacher's effect on the non-cognitive factor explains 63% of the teacher's effect on GPA. Same thing for being on time in 10th grade, only 2% for the test scores, about 40% for the non-cognitive factor. And of course, these two numbers are the same. For English, you pretty much come to the same conclusion. Teacher effect on the non-cognitive factor has very, very little predictive power for explaining the effect on test scores, but a lot of predictive effect to explain these other things. So this is kind of saying if these other things, if we think that teachers who improve these other things improve long-run outcomes, as the sort of the correlational evidence I showed you very early on suggests, then it suggests that we should sort of pay attention to this, and we should care about these teachers in some way. So the last piece of the puzzle is really, well, we know we have these potentially different kinds of teachers affecting different kinds of ability. How does that explain effects on long-run outcomes? So the best long-run outcomes I have are the graduation outcomes that I showed you, the dropout outcomes, which are measured 3 or 4 years after, and then some of these proxies for college going later on. So what I'm going to do is I'm just going to estimate the equation like before, where I'm going to replace the test score out, the short-run outcomes with the long-run outcomes. And I'm going to ask whether teachers who are higher predicted value added improve the long-run outcome, or teachers who have higher predicted effects on a non-cognitive factor predicts effects on the long-run outcome. And that's basically the test. So I won't go through too much detail. So what I'm going to do to sort of quantify how much more we can explain is as follows. So I'm going to estimate one model where I only include the teacher's effect on test scores. And then I'm going to estimate a second model where I include the teacher's effect on test scores and the teacher's effect on non-cognitive ability. And we can just think of this psi times theta hat j as the size of the predicted effect for teacher j. And you can basically compute the variance of that. And that's going to be sort of the variance of the predicted effect based on value added. And I can do the same thing by adding that piece plus the psi 2 non-cog times theta j non-cog. And that's going to give me a sense of how much of the variability in the long-run outcome I can explain using the teacher's effect on both the non-cognitive factor and the teacher's effect on the test score. And I just compare those two variance estimates, and that's going to give me a sense of what is the percentage increase in the variability that I can explain using the non-cognitive factor in conjunction with test scores relative to test scores alone. So that's basically what I'll do. So the first thing I'll do is show you what happens. So what I've done here is I've stacked the data. This is primarily for efficiency reasons. So I've combined both the math teachers and English teachers together. I'm going to break them apart later on, and you'll see why. So to get at the issue of to get around this conversation about, well, is GPA really cognitive or non-cognitive? Is this cognitive versus non-cognitive? I'm just going to show, everything. And put my hands above the table and say this is what's going on. So I'll show you what happens when I regress things scores, and then use the effect of the teacher on GPA, the effect of the teacher on suspensions, the effect of the teacher on absences, the effect of the teacher on being on time in 10th grade, and then finally the effect of the teacher on the composite non-cognitive factor, just to assuage any concerns that this is being driven by one individual variable being funny or anything like that. And as you can see, the effect on the GPA certainly predicts dropout. The effect on suspensions does. It's not statistically significant, but the sign is what we expect. The effect on absences is not significant, but it's what you expect. The effect on being on time in 10th grade is significant. It has the appropriate sign, and when we combine everything, we see that the effect on the non-cognitive factor does in fact explain effects on dropout above and beyond the effect on test scores. And if we compute the increase in the variability explained in models, I have two different models here. So one model includes school by year effects, some models don't. The one that does not include school by year effect, we can increase the explained variability by about doubling basically. And if we include school by year effects, it goes to like 70%. So this is a large effect. This is to say, if we thought it was really important that like test scores of predicted wages, then this means that this is probably somewhat important as well, and we should pay attention to these other outcomes, short-run outcomes. So this is doing, if we do the same, and this is just a specification check. So I've done exactly the same thing for the outcomes as I did for the short-run stuff. So the effect of test scores on predicted dropout, nothing. The effect on non-cognitive ability on predicted dropout, nothing. And then if we aggregate the teacher's effects at the track by cohort level, again, we see effects that are statistically significant at the 5% level for dropout. So this is sort of dealing with the selection of observables and unobservables that were a problem driving the results. If I do exactly the same thing, now where the outcome is high school graduation, things look pretty much the same. One difference is that the test score effect remains significant throughout all of the different specifications. But as you can see, many of these individual factors explain. The only one that is not significant is the number of absences, but GPA, suspensions, and being on time in 10th grade all independently predict these log-run outcomes. And of course, the non-cognitive factor, when you combine it, does as well. In this case, it increases the variability by about 86% and 75% depending on the specification. And again, if we look at predicted outcomes, we don't find any effects on predicted outcomes, which is encouraging. And we do find effects when we aggregate everything at the track by year level. If we break things down by subject, this is what they look like. So the basic takeaway from subject, and we can think about exactly how this selection of Algebra 1 might be affecting this. I don't know if it is or it isn't. If you look at algebra for algebra teachers, and we look at dropout here, you'll see that the test score effect is highly predictive of dropout in the anticipated direction. The non-cognitive piece does, it has the appropriate sign, but it is far from being statistically significant. So this is sort of consistent with the fact that we could barely predict a teacher's effect on the non-cognitive factor with her prediction on the effect of non-cognitive factor, so it's not surprising we can't predict her effect on long-run outcomes with it either, which might just be an indication that the teacher effect on non-cognitive factor for the math teachers is not very strong. If you do the same thing for English, we find exactly the opposite result. We find very large effects of the teacher's effect on non-cognitive factor, and once we condition on that, the effect of test scores actually is no longer significant and small. Same thing for graduation, we see the same basic story. That for algebra teachers, the test score effect matters a lot. For English teachers, the non-cognitive factor matters a lot. I'll also say that if you look at the literature on teacher effects, like for example, the Chetty paper, what they find is that even though English teacher effects on test scores are smaller than English teacher effects on math, than math teacher effects on test scores, the long-run effects of teachers are larger for English teachers or similar in size to those in math. So what that suggests is that the test score effects that there's something going on above and beyond these test score effects, and this might be one possible explanation. Sort of consistent with that interpretation. I think we had something that found that as well, right? Something similar? Yeah, exactly. I see. So this is all consistent with that basic general trend. So this is now just looking at secondary outcomes, predictors of college going. I call these secondary because I only have these outcomes for like 1 or 2 or 3 cohorts because they're later. I don't have the full data for them. So they're a lot less precise, but they all go in the direction we might expect. For English teachers, the non-cognitive factor predicts what the number of AP courses taken. It predicts whether you took the SAT, and it predicts whether you actually intend to attend a four-year college. For math teachers, the non-cognitive factor doesn't really predict anything, but the test score does predict whether you intend to attend a four-year college upon high school graduation. And if you look at the percentage of the variance explained, for some of these things, they're huge. So for SAT taking and intentions to attend college, for the English teacher effect, the variability, the increase in the percentage of the variability explained is 800%. This might just be that the base is really low, but it's telling you we can explain a lot more. And actually, I'll come back to this and just point this out. So for the English teachers here, for the effects on dropout and graduating, for the English teachers, we can explain the increase in the amount explained here. Okay, this 2,805 is a little much, but 392%. Over here we have 200%, 400%. So we're talking about an order of magnitude, maybe more than doubling, maybe tripling or quadrupling how much we can explain, which is exactly in line with Chamberlain's main result of the test score effect, measuring only about 25% of the teacher's overall effect. Now, this could still be an underestimate of how much they're affecting, because this is based on what I can explain. But this is sort of consistent with the idea that some of that 75%, or maybe a large portion of that 75% that Chamberlain is referring to, has to do with the teacher's effect on non-cognitive ability. Yeah. So now I think that's basically the main punchline. So I'll just talk about a few things. So one thing you might wonder is, does this non-cognitive factor really predict a different set of skills? So one might think, well, we know that test scores are measured with error. And if test scores are measured with error, then the teacher's value added also going to be measured with error. And maybe what's happening is that your effects on the non-cognitive factor is just picking up some residual, unexplained stuff because your main effect is estimated with error. So I'm going to test for that by saying, well, if that's true, then it should be that we can test for this by basically saying, well, if that's true, then when I have the predicted teacher effect, I can run a regression of a teacher's predicted English test score, of a teacher's predicted effect on English test scores on the student's actual test scores, and we know the coefficient of that should be 1. And if it's true that all I'm picking up is measurement error, then if I also include the teacher's predicted effect on the non-cognitive factor, that thing should have some predictive power. And when I do that, I find that, in fact, that's not the case. So conditional on a teacher's effect on test scores, the predicted effect of the non-cognitive factor is actually, first of all, it's a negative coefficient. It has the wrong sign, and it has a p-value of 0.44. And the effect is really, really small. So there's just no statistical evidence to support the idea that they're basically two measures of the same set of skills. It's much more consistent with this non-cognitive factor picking up a completely different set of skills. Another thing is, you might wonder from a policy perspective, do observable characteristics predict teacher effects on the non-cognitive factor? Much like the effects on test scores, the answer is no. And in fact, some of the things that we would expect to be positively associated with the non-cognitive factor actually are not. So this is basically if I run a regression where I predict years of experience, I run a regression of individual years of experience going from 1 through 30, an indicator variable for each distinct year, against the teacher's effect on the non-cognitive factor. What I find is that as you'd expect for test scores, there's a positive gradient, meaning that more experienced teachers improve test scores. When I do the same thing for the non-cognitive factor, it looks like there's no relationship. There doesn't seem to be any relationship between years of experience and the teacher's effect on the non-cognitive factor. So, and we do the same thing with a bunch of observed characteristics. Nothing seems to explain it. So I can't really tell you what it is, but I can tell you that it matters, which is not that dissimilar from the teacher value added literature, which does the same thing. This is showing you the same thing for English scores, and interestingly, it's actually negative for teachers who are more experienced. Now, I don't know if this is a real result. This is barely significant. I think the p-value on this is like 0.31, so it's not highly significant, but the data suggests that if anything, it's actually negatively correlated with experience. I don't know if that's a real thing or not. So, we're not going to get much traction from a policy perspective by trying to identify observed characteristics that are correlated with this. But I think there are some ways in which the findings here might be useful for policy. Clearly, yeah. So the first is that you might think, well, maybe we can use it the same way people use value added, and let's incentivize teachers to do better on the non-cognitive factor. Clearly, that's a stupid idea in this case, because yeah, it's like, oh, you'll get more money if your students have a higher grade in your class. Yeah, so you just inflate your stuff, just like CTEX or student evaluations. It's easy to do. No one's going to do that, right? So clearly, that's not going to be something that's going to be helpful here. But I don't think that that's necessarily a bad thing. The point is that if there is an identifiable set of skills or set of outcomes that we know predicts things long term, we can leverage that information. So the first thing is maybe there are other ways to measure student non-cognitive skills that are less easy to manipulate. I don't know what those things are because I'm not a psychometrician, but maybe those things do exist and they can be put forward. So you might think of some kind of survey that students fill out, or parents' evaluations or something like that. That might be something we can produce that would measure some of the same sets of skills that are much more difficult to manipulate, and then we could provide teachers incentive pay based on that. Another possibility is to actually just identify the practices that are associated with improvements in the non-cognitive factor. This is something that people have started to do with test scores. I think Bob Piana has some stuff where the first stage was to say, well, if we look at the kinds of classrooms that generate good outcomes, we know what those classrooms look like. Now let's actually do things to get teachers to do those things to make the classrooms look like those classrooms, instead of getting them to improve test scores directly. So we can do the same kind of thing here. We can see what classrooms look like, or what teacher practices are associated with higher values on these non-cognitive factor, or any other psychometric thing you can develop to measure the same kind of thing, and then promote those practices either through evaluation, training, or incentive pay. We don't have to use incentive pay, but we could if we want to. So I don't think that, so even though it's true that the policy relevance of this particular measure of non-cognitive ability is not immediately obvious, I think that it certainly has implications that can be used for policy. So to conclude, basically sort of presents a very simple two-factor model such that student outcomes are a function of both cognitive skills and non-cognitive skills. This is not a new innovation, but it's just borrowing some of the work. And I basically argue that you can use a mix of cognitive and non-cognitive short-run outcomes to predict a teacher's effect on long-run outcomes. I sort of document that teachers have economically important effects on test scores and on the non-test score outcomes. And teacher effects based on test scores only detect a small share of the teacher effect on the non-cognitive factor, and vice versa. So it's not the same set of teachers. It could have been, but it turns out that it was not, in fact, the same set of teachers. And the effects on the non-cognitive factor reflects unmeasured skills that are not measured by test scores, and we can increase the amount of the variability in the long-run outcomes induced by teacher quality to a large extent by including non-cognitive measures in addition to the cognitive measures. So I'm not advocating tossing out value added. This is not a critique of value added per se. It's just saying that, well, what it does well, but we can possibly improve it by 300% by doing something different. That's it.
You're clearly not saying to throw out value added, but I think there is also a lot of interest in evaluating teachers that don't have value added. So how does the non-cognitive factor do on its own?
Oh, you mean if you just include non-cognitive factor and did not include test scores?
Right.
Oh, it predicts the long-run outcomes as well, pretty well.
So do you think that that's something you would, I feel like you've dotted all the I's and crossed all the T's. Is that a potential implication?
Yeah, I mean, I think, yes, I mean, I don't know if we want to use this one per se, but I think certainly one implication would be that if you don't have test score measures, there are other things one could use to measure teacher quality. And, in some sense, you might argue that all I'm doing is taking a step away down, like taking a step further down the rabbit hole of trying to measure everything, right? So my critique is, well, test scores measure something, but they don't measure everything. So then it's a little bit disingenuous for me to say, well, here's another thing that measures something else, so let's just use that. Maybe there's something else and that's not measuring as well. So it's not obvious that the implication should be, well, just use my measure and everything's going to be honky-dory. It's entirely possible that this may be a marginal improvement, albeit a large improvement, but there may be something else that's not measured that is also very, very important that we should be thinking about. So I don't know that I wouldn't necessarily advocate saying, well, we can use this measure because it works pretty well. It's going to work better than nothing, right? So if you're just throwing darts at a board and determining who's going to be fired and not, then certainly using either test score value added or effect on a non-cognitive factor is going to be an improvement over that. Whether that's an improvement over other things that I just don't know. And that's going to be more than a empirical question. Yeah.
I find this to be really interesting, and in the interest of full disclosure, I'm in developmental and education psychology, so I'm going to come at it from that perspective. No problem. No, I find it really interesting because I'm glad that you were able to kind of pull out this other domain of interest. And so I want to ask you a couple questions that came to my mind that you might say, oh, that makes sense, or no, you're completely not thinking about it the right way. But one of the things is thinking about these non-cognitive skills, this category that you apologetically called non-cognitive skills, I understand. But it's, you know, if you're thinking about, you know, issues of suspension, GPA, and absence, they kind of map on well to some aspects of engagement. And there's work around those behavioral components of engagement in high school that actually, there's kind of like work that kind of describes how teachers can pull for that type of engagement in high school settings. And I'm curious, have you come across that or have thought about how that work links in at all?
So it clearly links in. I definitely looked a little bit at some of the literature, and my review may not have been comprehensive, to see like what these measures seem to be picking up. So the psychometric stuff that I found it seems to be like, so motivation is one. I think like grit was another one that seems to be associated with similar things, although there's some controversy about whether grit is really a valid measure at all. So I don't, yeah, so it does seem to be associated with stuff. It seems to be associated a little bit with some of the big five. You probably may have issues with that because that's not supposed to be very malleable, but it does change over time. So it does seem to be associated with, I guess, conscientiousness, I believe, and a little bit of, not so much open-mindedness, but I think there's another one that I forget, but conscientiousness was a big one that I think is associated with. As far as like what teachers could do to promote it, I don't know, but I think it would be fascinating to figure that out. So one thing that I would be really interested in doing, and aside from this study itself, is sort of getting a better sense of what the teachers are doing to generate these different effects. Like I've talked about teachers being different, and it would be great to know what about them is different we can observe, and maybe what's different is that the teachers who are promoting the the large effects on this sort of non-cognitive stuff are engaging in those behaviors that you're describing. And I don't know that, and I would love to be able to get my hands on a data set that would allow me to interrogate that kind of issue. And if you know it, please let me know.
That's really neat. Then the other thing that I was thinking about when you were describing, you know, these as teacher effects on non-cognitive skills, I was thinking, you know, by their very nature, these are adolescents, and we're talking about something in a social and emotional domain. And I'm trying to think about how these kids are placed into these classrooms and if some of what you might be picking up on are peer effects.
So it shouldn't be peer effects. So based on the way I constructed things. So the reason it shouldn't be peer effects is because the argument that I'm making is that you might be assigned to your track based on a lot of things, one of which might be your underlying level of non-cognitive socio-emotional skill, and your cognitive skill as well. And by looking to see not just whether there's so the thing that I don't do is just say, well, this teacher who's teaching in this track is high on this ability and low on that. What I'm doing is I'm saying I'm going to take a teacher and estimate her effect on all other years with a different set of kids and ask whether exposure to that teacher in a different year is actually associated with better outcomes. And by doing that, I'm essentially removing the actual peers, because I'm saying I'm estimating a teacher's effect using a different set of kids when she was in a different classroom, and I'm asking now whether you do better now. So mechanically, by the way I constructed it, not going to be based on the actual peers themselves. Does that make sense? And the simplest way to think about that is if you have a school where there's only one algebra teacher, and I'm basically saying, well, the teacher who came in 2005 is better than the one who was in there in 2006. The pairs hasn't changed systematically between 2005 and 2006, so if I'm finding effects using that kind of variation, it's not going to be driven by the composition of the classroom. Does that make sense?
Yes, that makes perfect sense. But there was one more. I'll let someone else go.
So I wanted to, so the way you've set this up and, thank you, framed this makes perfect sense to me in terms of dividing these into cognitive and non-cognitive, and I appreciate the point at, you were responding to Chris's question about being able to break down the non-cognitive things, but I'm wondering, in the same way that you think about, when you first started, I thought, well, there's multiple long-term outcomes we might be interested in.
Yeah.
And there are a variety of things that might predict some of those better than others.
Right.
And so in some sense, this becomes some sort of, if we're really wanting to get to the, if we ever get to the point, I think we can fine-tune this, right? We want to have some social objective function about how you then weight these things in a way to arrive at that.
Right.
But I'm wondering, and I maybe here and I didn't catch it, you may have covered it, but just along those lines, among the non-cognitive factors that you have, do you find some are better at explaining some of these long-term outcomes than others? And so, if so, how big are those differences, and do they rival differences between the so-called cognitive and non-cognitive things?
It's a good question. So the short answer is I don't really know. But so I think the best example to think of is like you want to predict effects on criminality versus earnings, and those are two different things. And I mean, we even saw it in terms of different points in the distribution. Like the same set of skills that are really important at the bottom are not necessarily the same set of skills that are important at the top. So even within the same variable, just at different points of distribution, we're getting different results. So there are definitely big differences. I don't know. I haven't compared that to the cognitive versus non-cognitive, but for sure, like when you're predicting crime, being suspended is a much better predictor of whether you end up being arrested than, say, whether you're late for class. GPA, I don't remember whether GPA predicts it or not, but I know that the biggest predictor of that was sort of whether you were suspended. In terms of predicting dropout, obviously on-time grade progression, which is almost like a leading indicator for dropout, is going to predict that to a large extent. Absence is also same thing, kind of like it's like a slow dropout is going to predict a lot more than, say, being suspended. So definitely there are differences, and they are important differences. And I think you're right in terms of if you really wanted to take this and run with it, we can say, well, what do we care about as a society? What is the objective? Is it to make students earn more money? Is it to make sure they don't earn lower earnings, or are we trying to increase earnings on average? Are we trying to make sure they don't commit crime? We can figure that out, and I've sort of set it up such that I didn't even say what the outcome was. I just said there was a long-term outcome, but it could be anything. And then you can decide what that outcome is, and then you can sort of use the apparatus and make it in a more flexible way and break away from like cognitive, non-cognitive, and just say we have a whole bunch of short-run outcomes. I want to find the set of weights for all these short-run outcomes that best predicts that, and that's going to be the way that I'm going to weight for something. I think that's. I think that we're so far from that, but I think that's. But I think in principle, that's totally what you would do.
Well, that is not that different from what the consortium is doing right now, too, right? I mean, because they did this analysis of CPS data, and they were looking at, I guess, predictors of dropout, right? And on time to 10th grade and attendance, I think, were the two major indicators, which is similar to what you observed here. Right. So that I have this intervention that basically they don't focus on teacher ends, but they focus.
Yeah.
I was just thinking about, do I really need this? I was just thinking about, you know, Rakesh, where he says if we cut off the bottom 10% of teachers, and I'm just trying to think through this. If there's no correlation between the very little correlation between value added and this non-cognitive.
Yeah.
I mean, do you see any? Does this shed any light on whether that's a harmful policy or not?
It does and it doesn't. So I think in these data, well, insofar as there is a different set of skills that is not correlated with your test score value added, then we have to start worrying about it. So at the very least, the results here suggest that it's something we should worry about and think about, because it depends entirely on what the correlation is of this other piece. Now, I would say that what I've done is I've documented that there is another piece, one other piece, and based on this one piece, the correlation is positive, which implies that if we were to just chop off the bottom 10%, we're probably going to do just fine. But that's not to say I couldn't have come up with some other set of outcomes that is negatively correlated with it, in which case it would go in the opposite direction. Because like I said, all I've done is said, here's another measure. I haven't said I've measured everything.
Right.
And if I haven't measured everything, it's always going to be a concern. But at the very least, the way that I've constructed things is to sort of do least offense to people who are really strong proponents of that. Because they review my papers.
I'm just curious, did you notice any patterns if you looked at just the lowest quartile of the non-cognitive skills, the 25 to 50, the third quartile and fourth quartile? Like, is there a certain level of these non-cognitive skills as you measure them that you consider enough, or what are your observations about just kind of those 4 quartiles?
Yeah. I don't know. So you basically asked me if I sort of parsed. And one thing I did do at one point was I actually had a scatter plot of the non-cognitive value added versus non-cognitive effect versus the cognitive effect or the test score effect. And I could have gone a little farther and like seen whether this thing is linear or non-linear or that kind of thing, and that would get a little bit at like maybe at the bottom quartile there's something fundamentally different going on than at the top in terms of the relationship between value added and the non-cognitive piece, but I haven't delved that deeply into that specific issue. But it's a good question, and it's something that's worth looking into, especially so if you start if I can get people to start believing this thing, then I think the next step is, well, what are the policy implications? I think that's thinking through that kind of issue is exactly where you want to go.
Thanks very